intrigued by your mind. I'm intrigued by your looks. I'm intrigued and beguiled. I gone and read all your books. Welcome back to Mind the Future. If you're enjoying this series, please make sure that you subscribe and smash that like button. Now, if you've ever looked up at the sky and wondered what the universe is all about, you're going to love our latest guest, Dr. Andrew Howell. Andy leads the supernovae group at the Las Cumbres Observatory and is adjunct professor at the Department of Physics at the University of California, Santa Barbara. In other words, he's an astrophysicist. Andy is one of the highest cited researchers in the world, the principal investigator of the Global Supernova Project, and has been instrumental to the discovery of several new classes of supernovae, including the first kilonova, which is a merger of two neutron stars, something that has been widely heralded as the biggest scientific discovery of 2017. Andy also appears on and hosts radio and television shows about science for outlets such as National Geographic, the History Channel, and the BBC. Perhaps a little more surprisingly, he's also an accredited film critic whose love of cinema inspired him to co-create the show Science vs. Cinema, which he hosts. On the show, he talks to both scientists and the cast and crew of films about the science portrayed in them. And he also regularly gives public talks about science or the science of film all over the world.
It's so great to have you here today with us, Andy, on Mind the Future. And before we start this conversation, I'm going to say it's very important to note that I don't even have probably like 1% of the depth of knowledge that you do on this subject or on physics. So my questions are basically going to be like a small reflection of my immense curiosity. How is that?
No problem.
Great. So, we're going to start off with an easy question. When you look up at the sky, what is it that you see?
Well, first I want to clear up one misconception about astronomy, and that's a lot of people think that what we do is like go out and look up at the sky. I know that's not what you're asking, but so people it really pisses me off in some print interview I was doing one the other day when I was just like, just don't use the word stargazers and whatever, because we just hate that, because everything these days is done with computers and with you're taking digital images, you're using satellites, all these other kinds of things. So there is this sort of romantic notion of the astronomer like going out and looking up, but everything that you can see with your naked eye is a star in the Milky Way galaxy. You can see a couple of other galaxies if you really know where to look, but just about everything you can see is a star in the Milky Way. And it's also just like, if you think of the galaxy, if it was like, say, this area, then I'm just holding my hands out a little bit, then the stars you could see would be like 1/50th or something of whatever area you're thinking about, just like actually even smaller than that, a tiny little region of the Milky Way. And then what I actually study are supernovae in distant galaxies, and they could be billions and billions and billions of light years away. So to put it in terms of like, say, light travel time, light from the stars that you see with your naked eye are like maybe tens or hundreds, maybe 1,000 light years away. But I'm looking at things that are some hundreds of millions of light years away or billions of light years away. So basically everything you see with your sky, it's been sort of studied to death. There are some exceptions. There are some reasons to study some of those stars, like to look for planets around them that we can only now do. But mostly what astronomers are concerned with are things that you can't see in the sky.
As a human being, though, when you look up.
Yeah, I mean, fine. Okay, sure. As a human, like when I was a little kid, I would look up and say like, oh, I wonder what's going on up there. Like each one of those little points is like another sun like ours. Maybe there's life around them. And, of course I saw like Star Wars as a little kid, and I was like, oh, that's what I want to go to those alien worlds and talk to some aliens, but then it turns out I'm like too tall even to be an astronaut. So I got to stick here on Earth and study those things. That's the next best thing. So I see like incredible possibilities of all kinds of other, maybe there's other civilizations out there. Maybe they know a whole lot more physics than we do, and they're very advanced. Maybe they're incomprehensibly different to us. We haven't found any of that yet, but we can still study the cosmos and all of the incredible physics that is just so different than what we can probe on Earth. Life on Earth is it's quite limited in what we see with our eyes and what we hear with our ears and everything else, and what we can even sample in a human lifetime. But out there, that's where you can really get to the laws of physics that you can't get to on Earth. So like black holes and like X-ray binaries and exploding stars and all of these things. We'll never be able to create some physics experiment on Earth that could probe that, but we can by using telescopes.
See, I didn't even realize that you were too tall to be an astronaut. I didn't know there was a standard. That's discriminatory a little bit.
Yeah, it's just you have to build things to meet an average person. And probably a good rule of thumb is if it's hard to find the right size pants in the store, then it's probably hard to find the right spacesuit size. But I did get to go in a spacesuit I was a host of a show on called Known Universe on National Geographic, and Mike Massimino, who's the tallest astronaut, I think, at 6'2", he said like, "Oh, let's put Andy in a spacesuit." He was the co-host, and so he got the NASA Spacesuit Lab people to like basically set it to his settings and then put in some extra spacers, and so I did manage to fit into one.
Right. Well, that's great news. So maybe one day there'll be spaceships, and
Yeah, the rules are always changing now with private spaceflight and other kinds of things happening. It may be that the height limits are increasing. I'm not sure.
Right. So one of your main areas of expertise is studying supernovae, and so I'm interested. What led you to be interested in that side of things?
Part of it is that it's just interesting to me that, stars can explode. Certain types of stars can explode anyway, and they can, create a black hole, and they can, or they can create a neutron star that is like, like the mass of the sun, but in the size in like 10-mile radius, like almost a black hole. Or they could be so bright you could see them across the whole galaxy. And it's something that's sort of dynamic and changing in astronomy, whereas a lot of things you study are static, like they don't change on human timescales. But this is something that just, bam, happens. So part of it was just, hey, they are cool. You can really probe physics that you can't probe on Earth. They do all these interesting things. And another thing was just that you can use them to actually map out distances in the universe. So with these, a certain type of supernovae, they're always about the same brightness, not exactly, but we can calibrate for that. And then you can use them to map out the history of the expansion of the universe. And so as I was doing graduate school, that was starting to be done for the first time. And they didn't have the results yet, but that's what eventually led to the discovery of dark energy. So that means that something is out there, some kind of energy that's making the universe expand faster and faster. And, everything that we are, normal matter, like you hear about in high school or whatever, is like 4% of the universe. But this dark energy is something like 72% of the universe. And so that's like the normal stuff in the universe. And we are just this really exotic thing. And so to me, that's like studying that stuff is like the frontier of human knowledge right now, where we found this new thing. We have almost no idea about it. And so like, that's where I like that. Those are the kinds of things I like to study, things that we just don't know very much about.
Right. That's really fascinating. I had no idea. I'm learning a lot from this. I hope everyone else is too, or maybe they're just smarter than me, so they're not learning.
No, it's like nobody's born knowing a bunch of astronomy knowledge. You have to learn it. And so that's why I like doing this kind of stuff. You get to explain to people, hey, there's cool stuff out there that you might not know about, but let me tell you.
Well, that's why I got into, even when I first started writing, I was always interested in interviews because you get to learn so much. And I always like to do a bit of research. So I would always learn a little bit before I would do those interviews. And then I get to talk to the most fascinating people who are really experts in their fields and question them. So that's an amazing opportunity.
Yeah, I have a show, Science versus Cinema, about science and movies. So I get to do that same thing where I get to interview people and ask people like that made some science fiction movie, say like, why did you decide to take those choices that you did? And then often they're very well thought through. Sometimes they're not. And then I go to the scientists and say, like, did they make these choices correctly? Or what's the real story here? So yeah, it's a lot of fun. I love to talk to like experts who really know what they're talking about.
Wow. So during your time as an astrophysicist, what would you say are the most significant or exciting discoveries that have been made? And I know you've also been part of a team that made one.
Yeah, quite a few, but, some of them are mundane-ish, and then some are like really quite profound. So the discovery of dark energy, like I mentioned it a few minutes ago, was discovered in the late 90s. And I didn't participate directly in the discovery of dark energy, but I then went to Lawrence Berkeley Lab soon after and worked with Saul Perlmutter there. And he's one of the people that eventually got the Nobel Prize for discovering dark energy. So we helped to confirm it while there. And then later I went to the University of Toronto, where I helped to start this group called the Supernova Legacy Survey. And we made the best measurements of dark energy that anybody had made up to that point. And they're still the backbone of the best measurements today. And that sort of told us that this is probably a property of the vacuum of space itself. So like, space doesn't have to have zero energy, even in, you think there's nothing there. It can actually have a sort of ground state energy. And that's what we think is happening, but we're not completely sure. So we're working on a satellite. NASA's working on a satellite to try to map out the dark energy even better. That's called the Nancy Grace Roman telescope. And that's going to be launched here in a few years, but that could really answer this question of what is dark energy. So that's one like very profound thing recently. Another one is the discovery of gravitational waves. So this is like when, say, two black holes are orbiting together, they actually make waves in space. And that was predicted by Einstein, but he thought we'd never see them because they're just so minute. They just change so they actually stretch and distort space-time, and those waves can pass through the Earth. And it changes things by kind of like the width of an atom or something like that. Not even like maybe the nucleus of an atom. And yet we can build these sensitive detectors. They have been built. There's 4 in the world right now, 2 in the US, 1 in Italy, and 1 in Japan. And they can actually sense these stretching and squeezing of space after 2 black holes, maybe hundreds of millions of light years away or tens of millions of light years away, merge together. The waves make their way through the Earth. And then using those detectors, they can tell us, look over there in the sky and see if there's an explosion associated with that. And so in 2015, the first set of black holes merging together was discovered in this way. And then in 2017, we found 2 neutron stars merging together to make a black hole. And so that made a new kind of explosion called a kilonova. And that type of explosion, it turns out, is responsible for most of the heaviest elements on the periodic table, like platinum and gold and things like that. And my group was one of 6 groups in the world that co-discovered the first kilonova. And so it's like remarkable to me to think that we didn't know where, huge parts of creation effectively came from until just a few years ago. And that was made possible by sensing the universe in a new way, by actually sensing distortions in space-time. So, every discovery leading up to that in astronomy was basically electromagnetic waves like light. And a few times we detected particles from other things, but now we've got a totally third way of doing things, and that's sensing space itself.
That's pretty incredible, actually. And just to think that Einstein didn't have a way to verify it and still made a prediction that ends up being true. It probably never found out whether that prediction was true in his lifetime. So, which is a little sad. But, how often does it even happen that, you have a theory or hypothesis and you're able to then actually conclusively prove that that's true?
That happens all the time in astronomy, where we hesitate to use the word conclusively prove or like language exactly like that, just because we, sort of think all knowledge is provisional. So that if you come up with an even more refined theory, you could show that that's wrong, but it's not necessarily completely wrong. So gravity is a good example where Einstein made a lot of his contributions. Newton had this theory of gravity that explains how gravity works largely to the extent that we can probe it on Earth. But Einstein just went a little farther and said, that's just a small piece of it. There's a greater theory out there that explains things in more extreme conditions. And then when we went and looked, we found that, that is right. And when you have a theory like that, then it can produce follow-on predictions. And then that's the whole trick, is then you go out and look and you see if all of those predictions are confirmed. And so far, general relativity, Einstein's greatest prediction has all held up with every prediction we've made, even into extremes that he could scarcely have conceived of. And it's remarkable, one of the most remarkable theories any human has ever come up with. But we know that it's limited. It can't handle quantum mechanics, so things at the very small level. And nobody's figured out a way to unify quantum mechanics and relativity. So we know it's incomplete, just like Newton's theory of gravity was incomplete. So, people are always looking for the next big theory like that. On the smaller scale, just even understanding like how a supernova blows up, we don't understand a lot of that. And so we model them on computers. And so sometimes our knowledge, like we know all of the physics equations, but we don't know then a star is such a complex thing. And when it goes to blow up, there's a lot of unknowns in the physics. So it's too much for the human mind to just work out with a pencil and paper. So we have to simulate them on computers, but even our computers are not fast enough. And so a lot of our knowledge is a sort of race between observations on one hand to find new things and just map out like what totally things that shock us and we can't explain and then for theorists to try to explain that, but also to just get the basics right. And so we're in this great state. It's this golden age of astronomy where we're developing new telescopes to see the universe in a new way. Anytime you can do that, you're going to make new discoveries. And then we're developing new computer algorithms and hardware and everything else to be able to compute the universe in a new way. And science works best when there's sort of this interplay between both of them.
What kind of technological advancements do you think will really help us make more discoveries about space? What's sort of lacking right now that would absolutely be a game changer?
Yeah, there's sort of two main ways historically astronomers have made progress. And one is just building a bigger and bigger telescope. So telescopes are all about the amount of light you can collect. People think of them as sort of light buckets. And so if you make the mirror bigger and bigger, then it's like making your eyeball bigger and bigger. You can see fainter and fainter things. So right now, the biggest telescopes in the world, optical telescopes, have about a 10-meter diameter mirror. 30 feet, something like that. But there's a few telescopes in the drawing boards that will go to about 30-meter diameter mirrors. And then you have to square that to get the amount of collecting area. So we're talking about big advancements and allowing us to see farther into space. Now, the other way you can do things is to see in different parts of the electromagnetic spectrum, like X-rays and ultraviolet light and radio and infrared. And the technology to do that stuff, well, even digital cameras only really came onto the scene in the late 80s and early 90s. And we're still in the tails of that revolution of being able to expand bigger and bigger detectors and see more and more of the sky in the optical part of the spectrum. Now, the X-ray and ultraviolet and other technology is a little behind the optical technology. So every few years, we come out with new kinds of detectors that allow us to see a little wider part of the sky and a little deeper in all these other areas. And so we're just able to see more and more of the sky. So those are the historical type innovations, but there's a bunch of new ones we're doing right now. And one is that the time domain of astronomy is pretty unexplored. So most of what you see in the sky is pretty static. Like a star is not going to change that much on a human time scale or a galaxy. But stars blowing up or planets orbiting other stars or the black hole at the center of a galaxy eating something and throwing out some explosions or jets of material. The universe does change on rapid timescales, but it can happen so fast that you miss it because you weren't looking there with your telescope at the time. So the new innovation now is people are surveying the whole sky like every few days, and that's revealing, or we're about to. We're right now observing big parts of the sky every few days, but people are about to start surveying the whole sky every few days. And that tells us, hey, look, there's something interesting. And then a bunch of people go and point their telescopes there and then see this new phenomenon. And so that's basically, just using the time domain as this new frontier. So like I said, anytime you can see the universe in a new way, you will make new discoveries. And so this is the total golden age of, planetary discovering extrasolar planets, supernovae, black holes, all this stuff that changes rapidly.
I mean, space exploration definitely comes with a price tag. It's always been something that's been a debate for NASA, for example, in terms of their funding, and telescopes, obviously, especially like really advanced ones that help researchers like yourself, they don't come cheap. So, does that strongly affect the kind of research you're able to do? Is there a community of like research, resource pooling amongst people in your area?
Yeah, that's a great question. I mean, so astronomers like to think sometimes okay, let's have a variety of possibilities here depending on what our budget is. And so we'll go for one big mission or telescope that costs a lot of money. And then we'll have smaller telescopes or satellites that cost a medium amount, and then some smaller things. And so we're always trying to rebalance that. And one way we do that as a community is there's a thing called the decadal report. And that is, it comes out once every 10 years. And the whole community, especially in the US, get together and can put in input by writing white papers. And then a sort of panel looks at those and decides on the priorities. And so we agree as a community, here's what our priorities are. Then we go to Congress and say, look, if we get this much money, we can do this. If we get this much money, we can do this. And so that we're speaking with a unified voice, because astronomers found out a long time ago, and physicists as well, that if everybody is just talking and it's some cacophony, then the politicians just won't pay attention. And so actually sociology is a big part of astronomy and astrophysics. You have to be able to work with others and work with others all around the world. There's all kinds of deals made between countries to work on satellites together. I lead a project called the Global Supernova Project that's more than 200 people from all over the world. And so it's just people. So we're able to pool our resources that way, because some people might have access to this telescope, this other telescope, and we can bring them together. So that's changing the sociology of astronomy as well. We're going from this regime where we were data starved, where you go to the telescope once a year for 3 days and you observe some stuff and you have your data and you take the rest of the year to reduce it and understand it, to being completely data rich now, where we have tons and tons and tons of data, and you can't do it all yourself. You have to work with other people to help you analyze the data. So we're now making tools to be able to share data more effectively and be able to make telescopes interoperate better. So that's a huge frontier right now with this time domain astronomy, like I was talking about. One of the issues is that the Earth is rotating. And so if you have a telescope, one big telescope in one spot, and you want to see something that just happened over there in the universe, well, maybe it's daytime where your telescope is. And so by putting telescopes all around the world and then networking them together into a network, as the Earth rotates, there will always be some telescope that's in the dark that could always be looking at that. And so we can share that information and now observe the universe in real time. And that's something we never could do before. And that's a relatively cheap innovation in the sense that you're just combining like a bunch of small telescopes with the network instead of just one big telescope. So it's like combining the internet and the telescope, two things that totally were game changers in terms of paradigm shifts to the world. I mean, like the telescope dealt a big blow to the Catholic Church, in Galileo's time, because you could show that the heavens weren't perfect and unchanging, and that helped. There was a ripple effect in society, and it really helped spur the Enlightenment and our modern way of scientific thinking and everything else like that. And the internet has obviously disrupted our whole lives, and so by putting them together, we can do things in a totally new way, and maybe save some money in the process. We can do the same kinds of things. We can do some ways. Using those tools, in some ways, we can do things better than we can with a space telescope that's really expensive. So like the Hubble Space Telescope, you can't observe something super quickly because it takes basically weeks for you to program where it's going to go. And they only upload the schedule once every 2 weeks or so. So there's a combination of using that really expensive space telescope and using cheaper, smaller things on the ground.
Well, I have to say, I wish that politicians could learn a thing or two from scientists about cooperation, right?
Yeah, like not all scientists always agree on everything, but we have, hard earned lessons about this. I mean, one of the things that happened back in, I think it was the 80s, was the superconducting super collider in physics. There was this big, huge physics experiment that was supposed to be made in the US, but I think what happened was some physicists got to bickering in public and, things like that. And then eventually Congress killed it because they, after having spent a huge amount of money, like digging tunnels and doing all these things, because they just didn't feel that people were unified. So, it doesn't take too many lessons like that before you start to say, okay, we're going to all work together. And that's tricky. It takes a lot of infrastructure to do that. And astronomers are still learning it. The physicists like to do big, huge projects. Like there's some projects that like IceCube where they're trying to detect neutrinos from under the Antarctic ice. They have these strings of detectors that go down like a kilometer or something underneath the ice. And it takes like 900 people to do that project. Whereas astronomers are typically, historically have been, a single astronomer goes to the telescope, takes some data, maybe you work on it with your grad students or something like that. But now in building bigger and bigger collaborations, we can do bigger and bigger things. And so we're still learning the sociology of how to work with each other. And physicists sort of have that down because they've been working in big collaborations. So now astronomers are working with physicists more, like in this LIGO project I mentioned. And so we're learning some of that sociology. They're learning some from us as well.
Right. Well, you mentioned that you have the issue of sort of, or the problem, or rather the opportunity of being more data rich these days. Would you say that, are you seeing any applications of AI in that area at all?
Oh, yeah. So a huge thing is big data. You've heard about it in Amazon, Google, these other kind of business contexts, but that's a huge thing in astronomy as well. So a lot of stuff is moving to the cloud, like a lot of our data centers and things like that. And so we have these more centralized hubs that people can share data on and also even analyze data in the cloud. But to go along with that, we have such huge volumes of data that humans can't keep up with it. And so we need to do machine learning, deep learning, these new kinds of algorithms. Those have had a revolutionary effect. And, I don't know, when you go and shop on Amazon or something and it recommends other things, or Netflix, or, these things enter our daily lives. But the same thing, but astronomers are using them as well. But we're using them to do things more like, if I get this spectrum where you split the light up into like a rainbow of some distant object and you don't want to know what it is, you can have this tool try to tell you what it is without a human having looked at it, and say that's a supernova of this type in this, at this distance, and so on. And so that's the only way you're going to build huge data sets and do things even faster, is by using these kinds of algorithms. But we're right in that phase where we're building all of these algorithms. In fact, astronomers have been at it a little longer than a lot of other people. Some astronomers have spun off businesses to do this, to help the business world and things like that. This happens a lot where you have some, basic research in astronomy that people are doing because they think it's cool or it could help us with some understanding some deep thing in the universe. And then it just gets spun over into the business world. Like, we're talking right now on some video conferencing system, and astronomers started using we're real pioneers of digital cameras and helped perfect that technology that then went over into the movie industry, things like your cell phone, all of that. And so anyway, as a result, all of these new algorithms that's a huge part. It's just as big as new technology.
It's quite amazing how technologies that are developed for very specific purposes or very specific industries then end up affecting everything. Now, with space exploration or and a lot of science, there's a lot of the research that goes on just to have the knowledge and to understand the world better, rather than always having a practical application. But ultimately, why do you think it is important for us to explore space?
Yeah, some of it is it's this frontier of unknown knowledge. And I think all humans are interested in this, like, okay, where did we come from? In the sense, I mean, religion is pretty big, and that's where somebody says, I've got the answer. But there's a bunch of different religions and they all have different answers. But in some ways, astrophysics or astronomy is like an empirical version of that, where we say, here's the best answer that we have for that. It's provisional. We get more data. We're going to change that. So that gets at something deep that humans care about. But beyond that, there are all of these spinoffs. So like, lasers affect our life all over the place, whether it's medical treatments or, making sure your car doesn't collide with another one, or, a million things, CD players and DVD players and so on. Well, the laser phenomenon was identified by physicists first and seen in space first, and was started to be discovered. And then, people built them on Earth. So, these kinds of things, you sometimes just don't know where they're going to come from. One example that I've heard used is if I told you to, like, in let's say the 1700s, to invent the light bulb, you wouldn't have known. You'd have just started thinking in terms of better and better candles. So you wouldn't have known even all of these leaps that would have to be made to get there, like just understanding electromagnetic radiation. That was pure physics. And then, look at electricity and everything else like that, then that, totally transformed the world. So and you just won't even know the leaps that will be made if you just thinking ahead. But by doing basic research, you will discover totally new frontiers.
And sometimes by accident.
Yeah, exactly. Like sometimes it's sort of directed and sometimes it's completely by accident. And sometimes people think, oh, that will have no practical application. And yet it turns out to change the world.
Yeah. Now, I mean, if a genie popped out of a bottle right now and instead of granting you 3 wishes, it offered you a different kind of deal. So it would ask you could ask the genie one question that you want to know the answer to, and it would tell you. What would that question be?
This is where I kind of feel like I almost don't know the question to ask, because like if I get the answer to one question, it would, make me ask another question. I mean, I think right now, the thing I really want to know is, what is the nature of dark energy? And I guess that's the reason I, work on that some of the time. How could there be the major component of the universe? And, we don't understand very much about it at all. I know why. It's because our monkey brains weren't evolved to understand this thing that only shows up at cosmic distances, like in the expansion of the universe. But I still don't know what that means fundamentally. Like, what does it mean about the origin of the universe? Okay, I take that back. What I would really want to know is how much life is there in the galaxy? Are we alone? Is there other life, and where is it? Because then we could communicate. We could hope to communicate, and then learn a lot more. Whatever my career is like studying these unknown things, but those aliens probably know all the answers, and so I would rather just talk to them and figure out the answer, and just know if we're alone. That has huge. Yeah, but it's super unlikely. It's unlikely if they've traveled somewhere, but that's true. They could be just like single-celled or something like that. But it's generally likely that they would be quite advanced if they could communicate at all, let's say. Because, we've only been able to communicate in some interstellar way for like 100 years, whereas, in 100 years is nothing compared to 13.8 billion years of the universe.
So the funny thing is, one of the questions that I ended up having for you was, what are the odds that we're not alone in the universe, and whether we're going to know, whether you think we might know that for sure in our lifetimes, if there's a chance of that.
I have done some SETI research that's searched for extraterrestrial intelligence. I did it as an undergrad. And it was just minor stuff about helping them pick stars to look at, to listen for signals. And so I think it's a low probability of success, but it's also a low cost, and the payoff is massive. So it's kind of like buying a lottery ticket. And in this particular, I don't buy lottery tickets normally, but in this particular case, I think it works well. Now, for alien life, I think almost certainly there's some out there, but the question is it close enough for us to really be able to communicate with it? Will we ever know? And that depends on how many civilizations there are and how long they live. So if you think about it, let's say like there's 100 civilizations in the Milky Way. Well, the Milky Way is a really big place, like 100,000 light years across just our galaxy. And so if the average distance between two civilizations is like, say, 10,000 light years, we're not going to be able to have a conversation in a human lifetime. And if there are a low number of them, then the average distance might be like that. But if there's a huge number of them, then maybe the average distance is like, 20 light years or 100 light years or something. And then we could hope to communicate with them. So, and how many there are depends on if they're overlapping in time with each other or not, because we've only been able to communicate for 100 years. But if we wipe ourselves out in the next, 100 years, which we have the means to do, we then, our civilization will effectively have had a time of 100 years in terms of the galactic communicability. And so that's nothing in this. So civilizations could be popping up and destroying themselves all the time. They just never overlap in time. Like maybe there was a civilization like ours, but it was really big 1 million years ago. So that's the real question. And that becomes a sociological question. Can we survive for like 1 billion year time scale to make us like, that would mean that if we're common, if we're representative, then civilizations are common.
I can't even imagine the life form that we might end up as in 1 billion years, like if we survive.
Yeah. Well, I think what we're most likely to discover then is a second generation life. Hold on, my dog here is trying to get the ball. I don't know where it is. Anyway, I think what we're likely to discover is second generation life, because we're on the verge of creating thinking machines right now, like artificial intelligence. And that could survive space travel much better than we could. We're just piles of meat, And so you put that on a ship and send it away for 10,000 years to another planet. And then it can duplicate itself. It can keep thinking it can turn itself off to save energy for the journey. And it could generate new versions of itself much faster than humans can reproduce. And as the computing power grows, it could, think exponentially faster, whereas we're not going to improve our brain power anytime soon. So I have a feeling that if we actually discover life, that's what it will be. And that's what our legacy will be. We will eventually wipe ourselves out, evolve into something else or whatever. But those things will stick around they have the potential to stick around forever and ever.
I wonder if our consciousness is something that we are going to be able to somehow upload onto those, AI kind of machines. And
yeah, see, that's like such a huge deal to us, but it means nothing to that generation of life, in that they will be able to transmit their consciousness all around or whatever, right? And will they even have the same kind of thing? Like, is it even a consciousness exactly? Like, we think of it as sort of some version of self-awareness and mixed with some other things. It's not quite clear. But what if you had a machine that could think super fast, could go and explore things curiously in the universe somehow and replicate itself, but didn't have the pedestrian human concerns of like, trying to find a mate or eat food or whatever. I mean, so it might be almost unrecognizable to what we call consciousness, but be out there and doing far more profound things than we can. So I think of it almost like an ant thinking, I wonder if I'll be able to upload my consciousness to a human, or whatever. And it's like, who the fuck cares, ant? All right. That makes no sense. And so like if you had the power to pull a mind back from, let's say, you were going to go and get a mind from the 1800s and you could just like revive them today. You wouldn't even care about doing that because you're just like, well, I could just make a new baby human right here today. I mean, there's no to me, it doesn't matter if I get one of the old ones or one of the new ones. We only care because we care so much about ourselves. But I don't know if the future, whatever we create, will care about that.
I think we definitely care about ourselves. And we do think that maybe that human essence, whether it's imperfect, is able to do some very interesting things and some very terrible things. And so we are kind of interested in, like, let's take that machine capability of AI and infinite knowledge and that very quick access to any knowledge and being able to transfer that and that life form, and then melt it with our sort of imperfect human minds and consciousness, whatever that is, which, yes, we haven't quite figured that out. And if we can do it, I mean, that's also a very specific kind of entity that we become.
Well, but look at, we're kind of doing that right now with Facebook and Twitter and social media and stuff like that, right? It's where we part of our communication has moved into this digital realm, and we can communicate much faster than we ever could. And turns out it doesn't work so well, right? Because our sociological progression goes much slower than our technological progression. So we haven't figured out how to interact like that and to make that stuff work out. So that same kind of catastrophe, and right now it's imploding our political system and everything else like that. And that kind of thing could happen if we just get brain silicon interfaces. That would allow you to remember a lot more, communicate potentially faster. But there's a whole lot of follow-on effects. It could be like, okay, now I just transmit knowledge to that person without having to speak, and I could transmit digital information without having to have my human eyes. And eventually, you very quickly would then evolve into something quite
Neuralink
different.
Is working on that, right? Neuralink.
Who is?
Neuralink with Elon Musk.
Yeah.
That's kind of what their aim is ultimately. He seems to have much more immediate goals with that than people might think the implementation would be ready by. But who knows? We don't know.
Get me started on Elon Musk.
Okay, we won't.
Astronomers
Let's get you started.
Really hate Elon Musk.
Really? Yeah. Okay. Oh, now I kind of want to know why.
Well, okay, it's because of the Starlink constellation of satellites that he's launching. So they're trying to launch 12,000 of them right now. This is to provide Wi-Fi through satellites. And but they're really screwing up all of our astronomical observations. So you can see them soon after they're launched. And if you can see them with your naked eye, they really wreck our deep telescope observations. And right now there's a few hundred, I think, but there soon will be 12,000, and there will be then more than there are stars visible to the naked eye. So if you go out at certain times of night, it may just be this like firefly swarm of these things. And so this is a natural resource that's available to all of humanity at the night sky. And of course, this deep knowledge that we're gathering from it. And, this billionaire can just go and ruin it with no real oversight just because, he feels like it. And it's not even clear the economics of that whole idea will even work out. I mean, it's been tried before, something similar with the Iridium satellites, and that company went out of business. There's another company trying it, OneWeb. They already went out of business. And so, and then who will be left to clean it up? You in fact probably can't clean it up very easily. If they do go out of business. So it's this classic just trashing the commons for personal advantage, and we all suffer.
Yeah, and not playing ball with the science community and not being part of that collective. So
yeah, they are trying now to retrofit some of their satellites and make new versions that aren't as bad, but you can't really solve the problem at this point. It's too late. We are working with them to try to mitigate the damage where we can. It's almost impossible.
So, let's switch topics. Let's switch gears to something that you do love and are a fan of, and that would be cinema. As you mentioned, you have a show that you host called Science versus Cinema, where you explore the portrayal of science in cinema and films. So I'm just wondering, in what ways do you think cinema influenced science the most?
It certainly does in inspiring people, especially through like science fiction films. So, I mean, I became an astronomer because I saw Star Wars as a little kid and Star Trek, and then thought, oh, that's so cool. And then, I can go out and make these discoveries. And I got to interview Patrick Stewart and say, I've got to do a bunch of cool stuff. And part of it's because I was inspired by you, and he just like got such a kick out of that. So like, and so that's like, well, that's great. He's like, I don't have very much education at all. I know little to nothing, but still he can make me very inspired. So that's one area. And I think, but even that whole, there's just something about movies to me that it can really transcend a lot of your day-to-day problems and put things into a bigger human context. And a lot of science can do the same thing. And so there's a lot of kinship there between, let's say you go to a film festival and you're seeing movies from all kinds of cultures and languages, and it's this discovery of life far outside of what your little tiny human experience. And that's the same thing that science is. And being able to do that through, say, watching movies, get this empathy for other people, then allows me as a scientist to go and, start a collaboration of hundreds of people from every continent and all different cultures. And it's remarkable to me that there again, even though this person may have grown up as a Hindu and this person as a Muslim and this person as an atheist, and we can all come together and come to one answer about how the universe works and transcend our culture and our tiny little provincialism, and therefore, like, I don't know, somehow transcend all the different boundaries of Earth. So I think they're similar in a lot of ways like that.
What sci movies do you think have managed to do the best job of predicting what our future may look like?
It's interesting because most movies aren't necessarily trying to accurately predict the future. They're trying to make a sort of straw man future that then they can, will service the plot. But some are way better than others. So if you look at like 2001, it's incredibly grounded, almost to the point of a lot of people find it boring at the beginning. I love it. Where it's just the mundane nature of going through like space flight and like sort of realistic generation of gravity. It's got to run this treadmill, things floating around and the sort of dull boredom of everyday life. But that is necessary to then take this fantastical leap at the end where you're introducing such an incredibly advanced alien life form that you almost can't comprehend it. You couldn't get there without grounding it in total realism. And that was still a projection, in the 60s of what space travel would be like, on up into at that time, 2001. So I love it when you can use it to both be accurate, but also as a tool to go to much more profound places. Another example where it only half worked and mostly didn't is Interstellar. Kip Thorne is a physicist who now has a Nobel Prize, and he's one of the guys that came up with this whole LIGO thing of sensing gravitational waves that I was just talking about. Amazing, astounding person came up with this idea for a science fiction movie. Jonathan Nolan, who went on to make Westworld, wrote the screenplay based on Kip Thorne's ideas. And Steven Spielberg was supposed to direct. That was grounded in physics that we know, allowed some speculative things, but didn't violate known physics, and was unbelievable in that first draft that never got filmed. It was just astounding. One of the best science fiction screenplays I've ever seen. And then that deal fell through with Spielberg. So Christopher Nolan came in to direct it, but had a different idea of what to do, jammed his very pedestrian science fiction ideas on top of the really profound ones that Kip Thorne had. And the result is this sort of Frankenstein movie where they did amazing things like calculate this black hole that it took like something like 25 people to do the calculations, and they used real relativity. They wrote 2 science papers out of it, and it produces this unbelievable thing on screen that we learned a lot from. And then they did these calculations about time going slower on the planet than it does in real life. All that stuff is accurate, but then they do stupid stuff like they launch things in an Apollo rocket and then land with the first stage. And then, it takes an Apollo rocket in this era to get off the Earth. That's fine. But then on the planet they're on, it has even higher gravity than the Earth, and they just take off in the first stage. Well, then why do you need the damn Apollo rocket? Like, there's so many stupid things like that they do, and those are all Christopher Nolan's ideas. And so this is, to me, it's like, okay, it's like if you had Einstein that wrote something, and and then somebody else from the time, like Howard Hawks or somebody, says, I'll just jam my ideas into it. It's like, no, you are just a normal person. Okay, Einstein is like, you should just take his ideas as they are. So but this is the problem in Hollywood, right? Is that a lot of people are these creative types, and they sometimes even have an aversion to math and science, and so they dumb down or destroy some of the ideas that are really brilliant. And I mean, the same is true for physicists, that they don't always have the most, narrative friendly ideas sometimes either. But I think there is room for something to blend them together. You can, astronomers and physicists and so on know about far more profound things than movie people probably do, because the universe is a far crazier place than humans are creative. And so, if you're just copying movies from the past, then you'll never come up with you'll miss all the awe and wonder that's really out there. So take the new Star Wars movies as an example. I asked J.J. Abrams before the 7th one came out, are you going to use any of the incredible discoveries we've made about other planets out there? And he just said, nope. And because then you see what he made. He just copied the previous planets from the previous movies, right? And I'm like, you could have had these, planets made of diamond, and planets evaporating from their stars, and all these, just like double planets in a new Tatooine in a crazy way where it's never nighttime on a planet, all these cool things. They just, didn't consult scientists. Although I did consult a little bit for Rogue One. So they're, they were a little bit more willing to listen to scientists.
That's so interesting, and just anger, a little bit maddening, I'm sure. I mean, go ahead.
Well, in these movies, you have $200 million or something sometimes to spend. And yet the thing that they get hung up on the most often when that kind of thing is happening is the ego and small-mindedness of some person at the top, whether sometimes it's a producer, sometimes it's the director. And they don't, think a little broader or even bigger than what they know. But a lot of people do. Like I've talked to a lot of other people, like Andy Weir, who wrote this book, The Martian, and then that turned into something. And he's had issues, not sure how something might work, and called me up, and wants to know about it. He's super curious, and then we'll, make things, use some of those really profound things, and that can be quite successful. So that's the thing, is a lot of Hollywood thinks of physicists as just people that shut stuff down. But we can also open up totally new realms of creativity. I mean, the Marvel movies are the most successful movie franchise in history. They talk to scientists all the time. And scientists, some of my friends have totally shot down really dumb ideas that never made it to a Marvel movie, and, helped save the movie. And so and that's partly because they're naturally collaborative enterprises. And I think that's another thing we can learn from science and physics, that the movie world could learn a little from too.
I think, as complex and fascinating and deep as astrophysics is, at the end of the day, as mere mortals might just look at the sky and see a shooting star, which I recently have, and be like, wow, that's really cool. And sometimes it's that spark that causes us to then be like, no, more curious about it. But it's that little magical moment. I'm going to close this fascinating chat with you with this question I ask everyone. And that is, what are you, Andy Howell, most excited about seeing in the future?
What am I most excited about seeing in the future? In what context?
It could be technology. It could be, a progress. Anything.
Well, there are some new space missions coming up, and some are in the drawing boards. One of them is there's a mission coming up. The Perseverance rover that is headed to Mars right now, and we'll get there next year. It has a drone helicopter on it. And that's just a technology test bed. But can you imagine like flying around Mars and getting these amazing images? And it also has microphones. So we get to get the rover going around and hear like actual, color images and sound, and then a helicopter to like survey the landscape for the first time. That's amazing. But in the farther future, people are planning a drone helicopter for Titan, which is one of the moons of Saturn. And that is a totally otherworldly place. There's already been a lander there. They just got a couple of shots, but the skies are like yellow. There's these hydrocarbon lakes and things. I mean, just truly alien. And to think that, that when that mission should happen sometime in the 2030s is when it should get there. But, that in my lifetime, we'll be able to have like helicopter drone images from Titan, from a truly other world. That is some like science fiction come true. So those kinds of things, thinking, and that's all just because of human ingenuity and cooperation and basic physics. And it must be said, politicians and a country working together to put the resources to say, we care about this, we care about basic exploration. Not in the sense of, old colonialism or extracting resources or anything else, but pure discovery. And so anytime we go to a new asteroid, go to a new planet, I always tune in and check out all the data. I just love it.
That sounds amazing. Well, thank you so much for joining me. It was awesome hearing you speak, and you have a lot of interesting things in your mind. So thank you.
Well, thank you. My pleasure. It's been great.